section, you make less what? You will make less mistake. Okay, you make less mistake on this. Okay. So if we are to compute, I'm going to compute the shear stress out, is exactly the same equation over here. I just control and I paste, is exactly the same value, whether you take from the top or you take from the bottom. Okay. Now, I know it's not very clear now, right? Some of you did not ask, but why is it? Okay, why is it? Why we are finding shear XY? Okay, why is it not shear XZ? Or why is it not shear YZ? Why is it shear XY? And I'm going to explain this. Okay, I'm going to explain this. Okay, I'm going to explain this why I need this. So if you look at the question over here, it did not really say, okay, what is the transformation? Okay. But I like to train you all to do this now, because later on in the 9-10 week, you have to know the direction, what shear you're looking for. Okay. So if you look at the transformation over here, this is your XY transformation. Okay. And then over here, this is your YZ transformation. Okay. And we know that we have a BY coming here. And this is how the Q will flow. Okay, so this is how your shear flow will flow. Okay, so what I'm drawing now, okay, all these arrows are your Q. Okay, all these arrows that you see are your Q, are your shear flow. Okay. So if we were to put an element, okay, if I were to zoom in, if I were to put an element, okay, I were to put an element, or yeah, I were to put an element down here. Okay, I have to put an element down here. So this is my element. I will use a different color. So this is our element now. Okay, so we just put an element down here. And then on the element, okay, if you ask me, Eugene, where's the element over there? Then I will draw a smaller rectangle. This is where our element is. Okay, this is where our element is. Our element will be not so thick, will be thinner a bit at this view. Okay. So now I'm going to draw this in 3D now. I'm going to draw this in 3D now. Okay. So in 3D, I have to draw my transformation first. So this is Y, right? This is X. And over here, this is our Z. So if I were to put in our element now, it will look like this. Okay, this is how our element will look like in 3D. So what we are finding is this shear stress over here. So we know that this is our BY coming down, right? So our shear stress is in this direction, right? So if you look at this plane that I'm shading in yellow now, right? This plane will intersect the what? The x-axis. So shear, the intersecting plane is x. So because when I draw the yellow plane here, it's going to intersect the x-axis. Okay. And this force over here, or this shear stress over here, is in the y direction. That is why we are looking for shear xy. And we know that if we will draw another arrow over here, this is shear yx. Okay, and shear xy is equal to shear yx. Are we clear? Okay, so this is why in 3D, okay, you draw it this way. That's why we are determining shear xy. Okay, now we are now going to determine. Okay, I'm just we are now going to determine the shear stress distribution now. Okay, equation. Okay, so next thing we're going to do is we're going to determine. Then we're going to determine the shear stress distribution equation. Okay, so let me get the diagram across again. Right. So now we are going to find the shear stress distribution. Okay, so we are going to focus on the flange first. Why we focus on the flange first? Because the thickness is equal to 0.16 meter. Okay, the flange has a thickness of what? 0.16. So now if we were to draw a centroid, now let me make this diagram bigger. Okay, so if this is our centroid, okay, and then our variable y, for example, stop here. Now hold on. Our variable y stops here. Okay, so this is our y, right? So this is the area of interest. Okay, and then we have now to find what is our y bar. So this green line I draw over here, this is your y bar. Okay, so this equation that we are going to form has limits. Okay, it is only valid where between 20 millimeters or 0.02 y and is less than 0.035 meters. Why? Because we know from the centroid this entire distance is equal to 0.035. Okay, so the equation we're going to derive is only valid in that range. And why in that range is because the thickness in that range is equal to 0.16 meters. Okay, that's why I call it the flange. Okay, so now we are going to find Q. Okay, first mobile area in the z-axis as the function of y. So this is width, depth, y bar. Okay, so we know that the width is equal to 0.16, right? Now the depth, okay, the depth, which is this depth over here, right, which is this depth over here, right? So this is the depth, right? So when you see the depth is equal to 0.02 minus y multiplied by, no, not 0.02 minus 1. It's equal to 0.035, okay, minus y. And the next one, so this is your width, right? This is your width. This is your depth. And now your y bar is equal to 0.035 plus by y multiplied by 0.5. Now, does this expression over here look familiar? And the answer is yes. Why is that? Because we derived this expression before, right? It's over here. C minus y, C plus y multiplied by 0.5. Okay. And B is the thickness, as we know. Okay. So that's all I've done. Okay. So I know C is equal to 0.035 minus y, then bracket 0.035 plus y, then multiply by 0. So when you take this out, this will be equal to 0.16 multiplied by 0.5 times by 0.035 times 0.35 is equal to 98 times 10 to the power minus 6. And then you have to minus 0.16 times by 0.5, 0.08 y squared. Okay. So that is the first moment of area distribution equation. Okay. So from here, directly, you can do shear xy as a function of y. This did not change. The y, the vy is 90. Now this is a function. Hey, come on. Times 10 to the power minus 6 minus by 0.08 y squared, and then divide by 5.8133 minus 3, and then now the thickness is equal to what? 0.16. Okay, so this will be equal to 90 power 3 times by 98 power minus 6 divided by 5.8133 power minus 3 divided by 0.16 is equal to 9.483 times 10 to the power 3 minus divided by 90 power minus 6 10 by 0.08 7.741 times 10 to the power 6. Okay. No, not times 10 to the power 6. Wait. 9.483. Oh, I did something wrong down here. Too much rushing. Okay, so this is power of 6. This is power of 6. And then this is power of 9. And then your y squared. Okay, so this is your shear stress distribution, and it's only valid between y is greater than 0.02, less than 0.035. Okay, I'm going to stop here. I post this week homework already, and it's due on not this Friday, next Friday. Okay, if that's the case, thank you for your time. I'll still stay behind if you have questions. Thank you.